Hey there, welcome to the Deep Dive. If you're anything like me, when you want to understand something complex, really understand it, maybe you're gearing up for a test or just determined to master a new field, you want to go beyond the
Yeah,
surface. You
absolutely.
want the definitions nailed, the properties down cold, and the key theorems etched in your mind.
Yeah.
That's exactly what we're tackling today.
Precisely. And you've brought us a really vital area, connectivity and planar graphs. These aren't just like abstract doodles on paper.
Yeah.
They're the backbone of so many things you encounter, from the network that brings you this audio to the design of the circuits inside your devices.
And our mission for this deep dive is to leave no stone unturned in understanding the foundational concepts.
Mhm.
Cut sets, the different ways a graph can be connected, and the fascinating world of planar graphs.
Right.
We're aiming for that level of clarity and detail you'd need to feel truly prepared, to explain these ideas to someone else. Or, yes, ace that exam.
So we'll start with cut sets and cut vertices, really dissecting their definitions, exploring their essential properties, and thinking about how they manifest in real-world networks.
Okay.
Then we'll move on to connectivity, both from the perspective of vertices and edges and how that leads us to the ideas of separable and non-separable graphs and the crucial role of cut vertices within them.
Hmm.
After that, we'll delve into the elegant concepts of fundamental circuits and cut sets, which are, deeply intertwined with spanning trees.
Right.
And finally, we'll immerse ourselves in planar graphs, uncovering what makes them special, the significance of Kuratowski's theorem, the power of Euler's theorem, and the intriguing concept of the geometric dual.
Okay, let's dive right into cut sets then. Now, the source material defines a cut set in a connected graph
Yeah.
as a set of edges whose removal makes the graph disconnected.
Mm-hmm.
But, and this is a key point to really understand, it has to be minimal.
Yes.
What does that minimality really mean for us?
That's the crucial filter. Think of it this way. If you have a set of edges that disconnects the graph, but within that set, there's a smaller subset that also disconnects the graph,
Oh, okay.
then the original larger set is not a cut set. A cut set is the absolute smallest collection of edges you can snip to break the graph into separate pieces.
Got it.
The source gives us some excellent examples from figure 421, ACD, ABG, ABE, FDHF, and even a single edge are all minimal.
Just one edge can be a cut set.
If removing just that one edge disconnects the graph, yes, like a bridge in a tree structure. They're minimal in that removing any fewer edges wouldn't disconnect it, which is obvious if it's just one edge.
And it specifically highlights that ACHD is not a cut set.
Right.
That's because, as the source points out, the subset ACH within it is already enough to disconnect the graph.
Exactly.
So minimality is about efficiency.
Yeah.
No extra unnecessary edges in the sets, like needing, I don't know, one specific wrench, not grabbing the whole toolbox when just that one will do.
That's a great analogy. You might also hear cut sets called other things: minimal cut set, proper cut set, simple cut set, even co-cycle. They're all getting at this same fundamental idea.
Which is?
The minimal set of edges whose removal increases the number of connected components in the graph. You remove a cut set, you're guaranteed to end up with at least two separate, isolated parts. No more paths between vertices in those different parts.
Okay. Now, the source provides another really useful way to think about this, using the concept of the graph's rank. It says a cut set is a minimal set of edges whose removal reduces the rank of the graph by exactly one.
Right.
For someone preparing for a test, understanding this connection to rank seems important. Remind us, rank is n minus k.
Yep. N vertices minus k connected components. So think back to our definition. A cut set is minimal and increases the number of components.
So k goes up.
Right. If you start connected, k at 1. Remove a cut set, now k is at least 2. So k increases by at least 1. Since rank is nk, rank must decrease.
And then by exactly one part.
That ties back to the minimality. Removing the minimal set of edges needed to disconnect ensures you only increase k by the minimum amount necessary, which for a connected graph breaking into two pieces means k goes from 1 to 2, and the rank drops by exactly 1.
Ah, okay. The example in Fig 4.1 showed rank going from 5 to 4.
Precisely. 6 vertices, initially 1 component, rank 5. After removing the cut set, 6 vertices, 2 components, rank 4. A reduction of 1. It locks everything together.
That link to rank really deepens the understanding. And there's another definition. based on partitioning vertices,
Yeah, this one's quite intuitive too. You can see a cut set as the minimum set of edges that bridge two distinct non-overlapping groups of vertices.
like islands and bridges.
Exactly. Imagine you split all vertices into group 1 and group 2. The cut set is the smallest set of bridges connecting group 1 islands to group 2 islands. Remove those bridges, and you can't get from one group to the other anymore.
The example ACD in figure 4.1 connects V1, V2, V6, and V3, V4, V5. Removing them isolates those two groups.
Perfect illustration.
And a neat little fact to remember. Every single edge in a tree is a cut set. Why is that so fundamental for trees?
Because trees are like the definition of minimally connected. They have exactly N1 edges, no cycles. So if you snip any edge,
It has to fall apart. There's no other way around.
precisely, no redundancy. That single edge is the connection for some parts, so removing it creates two pieces. It highlights their structural fragility, in a way.
The source also mentions why this matters practically analyzing vulnerabilities in networks. For someone studying this, why is finding these minimal disconnecting sets so crucial?
Well, think like a network designer. You want resilience, right? Internet backbone, subway system, power grid, whatever.
Yeah, you don't want it going down easily.
Exactly. Identifying cut sets shows you the critical links, the edges whose failure would isolate parts of the network.
The weak points.
The weak points. Knowing them lets engineers add redundancy backup paths, stronger connections to make sure things keep working, even if some of those critical edges fail. Like a key fiber optic cable, maybe. If that's a cut set, you'd want a backup route.
Okay, solid grasp on what cut sets are. Let's get into their properties. Theorem 4.1. Every cut set must contain at least one branch of every spanning tree. For exam prep, the why is key. Walk us through it.
Okay. Remember a spanning tree. It's that minimal connected backbone, connects all vertices, no cycles.
Got it.
Now imagine, just hypothetically, a cut set that didn't touch any edge from a specific spanning tree.
Okay.
If you remove that cut set, the entire spanning tree would still be there untouched in what's left of the graph.
And since the spanning tree connects everything.
The graph would still be connected, which contradicts the very definition of a cut set, something whose removal disconnects the graph.
So the cut set has to break every possible spanning tree pathway.
It has to intersect, yeah. It must contain at least one branch from every possible spanning tree.
Makes total sense. Now, Theorem 4.2 flips it. Any minimal set of edges containing at least one branch of every spanning tree is a cut set. How's the reasoning here?
Okay, so if you have a set of edges and you know this set nicks at least one edge from every single possible spanning tree.
Then removing that set must kill all spanning trees.
Right. And if no spanning tree can exist in the remaining graph, what does that mean?
It can't be connected.
Yeah.
Because a connected graph always has at least one spanning tree.
Exactly. So removing that set must disconnect the graph. And the minimal part just ensures we didn't throw in extra edges. Every edge in the set is needed for that guarantee of hitting all spanning trees.
These two theorems really lock down that relationship between cut sets and spanning trees. Very neat.
They do.
Okay, Theorem 4.3. This one feels a bit different. Every circuit has an even number of edges in common with any cut set. For someone studying, what's the key insight?
The key is remembering how a cut set partitions the vertices. It splits them into at least two separate groups, V1 and V2, say.
Right.
Now, think about a closed loop. If that whole loop stays entirely within V1 or entirely within V2.
Then none of its edges cross between V1 and V2.
Correct. And the cut set only contains edges that do cross between the partitions. So in this case, the number of edges they have in common is 0.
And 0 is even. Okay, that case works. What if the here's circuit does cross?
Because it's a closed loop, if it starts in V1 and crosses over to V2 using an edge from the cut set.
It has to get back to V1 eventually to close the loop.
Precisely. And to get back, it must cross from V2 to V1 using another edge from the cut set. Every time it crosses out, it must cross back.
So it always uses the cut set edges in pairs.
Essentially, yes. So the total number of edges it shares with the cut set has to be an even number 0, 2, 4, and so on.
The source examples with circuit C1 and different cut sets showed intersections of 0 or 2. Seeing it laid out helps.
Absolutely. Examples make abstract ideas much more concrete.
All right, let's shift focus now to connectivity and separability. We've got vertex connectivity and edge connectivity. Important distinction for studying, right?
Yeah.
How are they defined?
Vertex connectivity, often written here, is the minimum number of vertices you need to remove to either disconnect the graph or just leave a single isolated vertex.
So it's about node failure resilience.
Exactly. Higher vertex connectivity means it's tougher to break by removing nodes. The source notes a tree has key 1 because removing any internal node disconnects it.
Okay. And edge connectivity.
That's the minimum number of edges whose removal increases the number of connected components. In other words,
It's the size of the smallest cut set.
bingo! We just spent time defining cut sets. Edge connectivity is simply the size of the smallest one you can find. The source also notes it's the minimum edge removal needed to reduce the rank by 1.
And for a tree, lambda is also 1.
Also 1, yeah. Remove any single edge and it disconnects. Good basic example to remember for tests.
So vertex connectivity, removing vertices. Edge connectivity, removing edges. Both measure how tightly knit the graph is. This leads to separable and non-separable graphs. How do they relate?
A connected graph is called separable if its vertex connectivity is 1.
Key, meaning there's at least one vertex whose removal disconnects it.
Exactly. Those are the vulnerable points. A non-separable graph has vertex connectivity of 2 or more, Q2. It's more robust. You need to take out at least 2 vertices to break it. More redundancy.
And this brings us to the cut vertex, also called cut node or articulation point. Sounds like it's the defining feature of a separable graph.
It is. A cut vertex is that vertex in a separable graph whose removal increases the number of connected components. It's that single point of failure.
Like the internal nodes in a tree we mentioned.
Exactly. The source says in a tree, every vertex with degree 1 is a cut vertex. Leaves aren't. Removing them doesn't disconnect anything else.
The source mentions figures. It's a good reminder that actually drawing these different structures highly connected, sparse, with cut vertices really helps understanding.
Oh, definitely. Sketching examples yourself while studying is invaluable.
Now, Theorem 4.4 gives another way to spot a cut vertex. V is a cut vertex if and only if there exist 2 other vertices x and y, such that every path between x and y goes through V. That if and only if is key for tests. Let's break it down. First, if V is a cut vertex, why must such x and y exist?
Okay, if V is a cut vertex, removing it disconnects the graph. That means some pair of vertices, call them x and y, that were connected before are not connected after V is gone.
Right.
If there was still a path between x and y that didn't use V, then removing V wouldn't have disconnected them. So every single path that originally linked x and y must have passed through V.
Okay, that direction makes sense. Now the other way. If every path between some x and y has to go through V, then V must be a cut vertex. Why?
Well, if all routes from x to y are forced through V, what happens when you remove V?
Well, those routes are gone. X and Y become disconnected.
Exactly. Which means removing V increased the number of connected components by separating x and y at least. And that's the definition of a cut vertex. It's a really practical way to identify them by looking at paths.
A very powerful tool for finding those single points of failure.
It is. And the source connects this directly to network design. You want resilience, so you want high connectivity.
Right. The example comparing 2 networks, same number of nodes and edges, but different connectivity. The highly connected one was much more robust to failures.
Absolutely. That redundancy from higher connectivity means more alternative paths, more tolerance for failures. That's the goal in robust design.
Okay, now some theorems about limits on connectivity. Theorem 4.8. Edge connectivity can exceed the minimum degree. Why is this upper bound true?
Think about the vertex, let's call it Vmin, that has the fewest connections. Its degree is DE.
Okay.
If you just remove all the edges connected directly to Vmin, how many edges is that?
That's the G edges.
Right. And what happens to Vmin?
It's completely isolated from the rest of the graph. Disconnected.
Exactly. You've disconnected the graph by removing edges. Since edge connectivity is a minimum number of edges needed to disconnect, it can't possibly be more than this number. So Y.
Makes sense. The weakest point dictates an upper limit. Then Theorem 4-9. Vertex connectivity is always less than or equal to edge connectivity.
What's the intuition here?
This one's a bit trickier. The core idea is take a minimum edge cut set. Sign set. These edges disconnect the graph. Now think about the vertices these edges are attached to.
The endpoints.
Right. You should be able to achieve disconnection by removing some of those vertices instead. By removing at most one vertex for each edge in the cut set, you can effectively remove all those edges.
So you'd need to remove at most a vertices to achieve disconnection.
At most, yeah. Sometimes fewer vertices might cover all the edges in the cut set. Since I is the minimum number of vertices needed to disconnect, it must be less than or equal to this number. Hence, R.
Okay, I see the link. And from this, a corollary. Every cut set in a non-separable graph with two vertices needs at least two edges. Why is that false?
Well, what's a non-separable graph?
Vertex Connectivity Kuro 2.
Right, and we just said Kiro. So for a non-separable graph, A must also be OA 2. And A is the size of the smallest cut set.
Exactly. So if the smallest cut set has size O2, then every cut set must have at least two edges. If there was a cut set with only one edge, O would be 1, implying A1, making it separable a contradiction.
Got it. Finally, Theorem 410 gives an upper bound on vertex connectivity. A floor, 2En. Where does that come from?
It's related to the average degree. Remember, the sum of degrees is 2e.
Yeah.
So the average degree is 2En. Vertex connectivity has to be less than or equal to the minimum degree, which in turn must be less than or equal to the average degree.
So the average sets a kind of overall limit.
Pretty much, you can't have super high vertex connectivity if, on average, vertices don't have that many connections. The floor function just makes it an integer, and the source notes this bound can actually be reached in some graphs.
So these theorems give us really useful bounds on connectivity based on basic graph properties like edges, vertices, and degrees. And the final note, K connected means K, and one connected means separable, just terminology.
Exactly. Good to have the language straight.
Okay, let's pivot to fundamental circuits and fundamental cut sets. The names suggest they're, well, fundamental.
And tied to spanning trees, right?
Hmm.
For someone studying, what's the core idea of a fundamental circuit?
Right. Start with a connected graph, find a spanning tree that minimal connecting no cycle structure.
Okay.
Now take any edge from the original graph that was not in your spanning tree. We call that a chord.
An extra edge.
An extra edge, yeah. If you add just that one chord back to the spanning tree, what happens?
You create a cycle because the tree already connected the chord's endpoints.
Exactly.
Okay.
And because you only added one chord, you create exactly one cycle. That unique cycle, formed by adding one chord to a spanning tree, is the fundamental circuit associated with that chord and that specific tree.
Clear. Spanning tree plus one chord equals one fundamental circuit. Now, fundamental cut sets. What makes a cut set fundamental?
Also defined relative to a specific spanning tree. This time, take your spanning tree and remove just one of its edges, a branch.
Okay, that splits the tree into two pieces. Right. Two sets of vertices. Now look back at the original graph. The fundamental cut set associated with that branch you removed is the minimal set of edges in the original graph that disconnects it in exactly the same way, separating those same two sets of vertices.
And what edges are in this fundamental cut set?
Critically, it will always contain the one branch you removed from the tree, and it might also contain some chords, those extra edges from the original graph, that happen to connect the two vertex sets separated by removing the branch.
The source examples help here. First one, tree is just edge AD. Cut set AD, BC, AC, BD contains AD, the one branch, and separates things the same way. So it's fundamental relative to AD.
Perfect. And the second example, with the heavy lines for the tree, removing branch splits the tree. The cut set DEF in the original graph separates the same vertices and contains only branch E from the tree. So DEE is the fundamental cut set for branch E. Similarly for HGF being fundamental for branch H.
Got it. Now, a theorem mentioned, the ring sum of any two cut sets is either a third cut set or an edge disjoint union of cut sets. Remind me, what's a ring sum?
Ring sum, or symmetric difference of two sets A and B, written AB, is the set of elements in A or B, but not in both.
So everything except the intersection.
Exactly. For cut sets, which are sets of edges, S1L2 contains edges that are in S1 or S2, but not common to both. The theorem says this resulting set of edges is either another single cut set itself, or it breaks down into several cut sets that don't share any edges.
That sounds a bit abstract, but hints at some algebraic structure.
It does. It relates to how cut sets correspond to vertex partitions. It's a deeper property. But then we get theorems directly linking fundamental circuits and cut sets.
Yeah.
Like a chord C that makes fundamental circuit is in every fundamental cut set associated with the branches in A and no others. This reciprocal thing seems key for studying. Why is it true? Okay, let's unpack that. Chord C plus some tree branches forms the fundamental circuit. Now, take any branch B that's part of E. It has a corresponding fundamental cut set, SB.
Okay.
The theorem claims that our original chord C must be an SB. Why? Think back to Theorem 4.3.
Even number of edges common between any circuit and any cut set.
Right. Consider our circuit O and the cut set SB. They definitely share branch B. That's one edge. If SB did not also contain chord C, they'd only share one edge. odd number.
Which violates Theorem 4.3.
Exactly. So for Theorem 4.3 to hold, the chord C must also be in the fundamental cut set SB, making the intersection size 2 or more if they share other edges, but always even.
Ah, that connects it. And the second part, chord C is not in fundamental cut sets tied to branches outside of oval.
Correct. That chord C only interacts in the specific way with the fundamental cut sets associated with the branches that form its fundamental circuit. It's a unique relationship.
The example with spanning tree BCEHK and chord F making circuit FEHK, it showed F, was in the fundamental cut sets for EH and K, but not others. Really illustrates it.
It's a perfect example, and the source notes the converse is also true.
Which leads right into Theorem 4.6. A branch B defining a fundamental cut set S is in every fundamental circuit associated with the chords in S and no others. This is just the flip side.
Exactly the flip side. If branch B and some chords make up the fundamental cut set S, then that branch B will be part of the fundamental circuit created by each of those chords in S. And B won't be in fundamental circuits created by chords not in S.
It's beautifully symmetrical.
It is. These two theorems really nail the duality between fundamental circuits and fundamental cut sets relative to a spanning tree. Mastering these is key to understanding graph structure deeply.
Absolutely. Provides a powerful analytical framework.
Definitely.
All right, let's move to our final topic. Planar graphs. This seems more visual. Can we draw a graph flat without edges crossing?
That's the core idea. A graph you can draw on a plane with no edge intersections is planar. If you can't, no matter how you try, it's non-planar. The actual drawing without crossings is called an embedding.
And right away, we meet Kuratowski's two famous non-planar graphs, K5 and K303.
The classics. K5 is the complete graph on 5 vertices, everyone connected to everyone else. K33 is the utility graph. 3 houses, 3 utilities. Try connecting each house to each utility without pipes crossing.
Can't be done right.
Can't be done. Theorem 5.1 proves K5 is non-planar, usually by starting with a 5 cycle and showing you inevitably get stuck trying to add the internal star edges without crossing.
Yeah, I remember trying that puzzle. You always end up with one edge that has to jump over another.
Yes, and Theorem 5.2 states K33 is also non-planar. Similar reasoning leads to an unavoidable crossing.
The source lists key properties. Both regular, K5 degree 4, K3 degree 3, both non-planar, but removing just one edge or vertex makes them planar.
Right.
And K5 has the fewest vertices, 5 for non-planar, K3 the fewest edges, 9. They're like the minimal forbidden minors for planarity.
That's a great way to put it. They are the fundamental obstructions to planarity.
Then we have different representations.
Yeah.
Straight line and plane representations.
A cool fact is the straight line one. Any simple planar graph, no loops, no parallel edges, can actually be drawn using only straight line segments for edges and still no crossings. Very clean.
And a plane representation.
That's just any drawing of a planar graph on the plane. When you draw it, the edges divide the plane into distinct areas or regions. We also call them faces. One region is always the outside infinite one.
And these regions are important for Euler's theorem.
Hugely important.
Yeah.
Euler's theorem is maybe the most fundamental result for planar graphs. It connects the number of vertices, n, edges, e, and faces, f, in any connected planar graph with a simple formula. E, n plus 2 equals f.
E minus n plus 2 equals f. That's amazing.
Yeah.
How is it proved, roughly?
The proof often uses induction. It shows the formula holds for a single vertex or a simple tree, and then demonstrates that adding edges or vertices in ways that keep the graph planar maintains the relationship. It reveals a great structural constraint.
It really does sound elegant. And from Euler's theorem, we get useful inequalities, like ELA 3 indices.
Yes, for simple connected planar graphs with D2. This comes from noting that each face must have at least 3 edges on its boundary, and each edge borders at most 2 faces. Combining this, 3F2E, with Euler's formula FCM plus 2, leads directly to E3N6.
And this is useful for proving nonplanarity.
Very useful. It's a quick check. If a graph violates this inequality, it cannot be planar. Let's test K5, N5E10. Is 10A35 6, that's 10E9, nope.
False. So K5 must be nonplanar. Algebraic proof.
Exactly. Quick and clean.
And there's a tighter one for bipartite graphs like K303 without triangles. E to 204.
Right, because in a bipartite graph, the smallest cycle is length 4, so each face must have at least 4 edges. This leads to the tighter bound. Let's test K3 by 3, N6E9 is 9 era 26 4. That's 9A also false.
So K303 is confirmed nonplanar by this inequality too. Very handy tool.
Definitely good shortcuts to remember.
Our final concept, the geometric dual G. Sounds like creating a new graph from a planar drawing. How's it work?
Given a planar embedding of G1, Put one new vertex for G inside each face region of G, including the outside one. 2. For every edge in G that separates two faces, draw an edge in G between the new vertices you put in those two faces. This new edge crosses the original edge once.
Okay, so faces become vertices, shared edges become connecting edges. What about weird cases like loops or pendant edges?
Good question. A self-loop in G around a face becomes a pendant edge in G attached to the vertex in that face. A pendant edge in G sticking into a face becomes a self-loop in G at the vertex in that face. And parallel edges in G become series edges in G and vice versa.
Seems like a complete transformation. What are the key relationships between G and G?
Lots of important ones. Self-loop in G, a pendant edge. In G, pendant edge in G, or self-loop in G, series edges in G, parallel edges in G. Parallel edges in G are a series. Edges in G, degree of a vertex in G is a number of edges bounding the corresponding face in G. G is always planar too. The dual of the dual, G, is essentially G again, if G is connected. And importantly, vertices in G, faces in G, faces in G, edges in G, edges in G, edges in G. They swap roles.
Wow, that's a really tight relationship. It's like looking at the same structure from the perspective of faces instead of vertices.
Exactly. It's a powerful concept in planar graph theory. And Theorem 510 mentions all duals of a planar graph are two isomorphic.
Meaning they have the same core connectivity structure even if they look slightly different?
Basically, yes. Different drawings might give slightly different looking duals, but their fundamental block structure will be equivalent in this two isomorphic sense.
And the source ends by mentioning university questions, reinforcing that these are foundational concepts for further study.
Absolutely. These topics form the bedrock for much of advanced graph theory and network analysis.
Wow. Okay, we have covered a lot of ground today. A real deep dive. Cut sets, connectivity, separability, cut vertices.
Fundamental circuits and cut sets. They're linked to spanning trees.
And then planar graphs, K5, K33, Euler's theorem, those inequalities, and the geometric dual. For anyone studying for a test, hopefully that laid it all out clearly.
And the key thing to take away is how interconnected it all is, right? Cut sets define edge connectivity, spanning trees linked to fundamental circuits and cut sets. Euler's theorem governs planar graphs. Seeing those links makes the understanding much deeper.
So as you, the listener, go forward, maybe think about networks you see every day. Social networks, roads, the internet. How connected are they?
Yeah, what are their potential cut sets or cut vertices? Would making them planar even make sense, or is non-planarity essential for their function?
Right. Like, consider the trade-offs. Maybe a super connected communication network needs to be non-planar for all those links. But a city's road network might prioritize planarity for simplicity, even if it means fewer connections. How do the ideas we discussed help analyze those strengths and weaknesses?
That's a great way to think about applying this. Graph theory gives us the language and tools to analyze these complex real-world systems. Keep exploring these ideas.
And if you hit other complex topics you want us to tackle in a deep dive, let us know. Thanks for joining us today.